Hello and good day. So for today's topic, we're going to discuss the first Maxwell equation, also known as Gauss's law, which coincidentally is, of course, a phenomenon wherein an electric field passes through a surface or is contained within a space, which is what we call electric flux. Okay, so for this first half, we're going to focus on surfaces of objects, be it a two-dimensional or a three-dimensional one. And then we're going to discuss volumetric flux on to the next video. Okay, so what we want to understand is what Gauss law is, then understand, of course, electric flux as well, then finally to be able to solve problems that involves Gauss's law. Okay, so first, what is electric flux? So it is the measurement of flow of electric field through a surface. So very self-explanatory, you know. So let's say you have a surface that is like this. Okay, say good old rectangular, square surface. Okay, so assume that's a flat surface that's placed on top of something. Okay, then an electric field passes through it. Okay, so let's say this is your electric field. Okay, so this will be your electric field. All right. Then the surface, of course, has a certain dimension, which will, of course, we will call the area. So that will be the total surface coverage of the object where the electric field passes. Okay, so of course there will be electric field passing here, then there will be electric field that's passing here if, let's say, the source is from a uniform electric field, something like that. Okay, say something like this. But of course, the places here are not our concern, because electric flux only deals with the electric field that passes through a surface. So only the area where there's the paper. Got that? Okay, so let's continue. Okay, so mathematically, electric flux is defined as this. Okay, so can be written as phi, that's capital Phi, okay, equal to electric field cosine phi, so this is small phi, multiplied by the area. Alright, so this is, of course, the electric field that's passing through the surface. Of course, the unit is in what? Newtons per coulomb. Then this one, of course, is the area of the surface, which of course has a unit of meter squared. So as you can see, since this is multiplication, the final answer would have the unit of Newton meter squared per coulombs. Okay, so there you go. As you're seeing, we have the trigonometric function here, which I will be explaining as to how we have obtained that value. So if you have visited the introductory place of the Canvas course, the reading part, So we have several orientation of finding the electric flux. So I'm going to show it to you here. Okay, so let's say for the first one, what we are going to move is the electric field. Okay, so I'll be drawing three surfaces now. Alright, so this will have three ways wherein the electric field will pass. So the first one will be, in the case of the first one, we will be drawing the electric field by passing to this direction. Okay, so just assume that electric field is passing through the object. Okay, so this is our electric field, and of course the area is this paper. Okay, the second one will be if the electric field is directly passing parallel to the surface. So the first one is perpendicular, the electric field is perpendicular to the surface. So the next one will be when the electric field is parallel to the surface, so it means it's passing through, right? So for the first one, it's the electric field are perpendicular. Here they are parallel with the sheet. Okay, then the third one, of course, if your electric field is angled at a certain degree. Okay, so let's say it will be passing at an angle of, let's say, 45 degrees. Now let's do it on the opposite side. Okay, something like this. Still, it will be 45 degrees now. So, like this. Okay, so there you go. Let's say the electric field is passing through the surface at this direction. Let's draw the arrow better. There you go. So it will be angled at a certain way. Okay, so if this is your surface, say this is your surface now. This is the measurement of, the plane of the surface. So that would mean that there is an angle here, which we will call, of course, theta. We're very familiar with theta, right? But if you remember the formula, it was written as phi. So where are you going to place phi? Okay, so phi would be an imaginary line, which we call the normal line. So the normal line is an imaginary line that is perpendicular to the surface of the object. So let's say this is your surface. The normal line would be this line. Okay, then I'm going to draw another one here so you would know. So it emerges from the center. Okay, or actually it's just an imaginary line. Just imagine an imaginary line that is perpendicular to the surface. If you remember from General Physics 1, we have the normal force, right? The normal force is perpendicular to the surface of an object. So basically, normal line is that exact idea. It's perpendicular to the surface of an object. Alright, so if this is theta, then your angle, which is in this case angle phi, alright, would be the angle between the normal line and the electric field, which is this. Okay, so if this is your normal line, then you're going to start from that, so that's the y-axis, right, going to the terminal side of the angle, which is of course the place where the electric field is drawn. So in this case, this is your phi. Okay, same goes for the other measurements here. So if in this case, this is your phi. Okay, then for this one, your phi is directly what do you call this, coinciding with the electric field, right? Let's make the arrowheads of this cleaner. Okay, so your first example, so this for the first example, let's calculate the electric flux of this one. Okay, so you would have an idea. So electric flux is what? Electric field cosine phi times the area. So in this case, phi is what do you call this, coinciding with the electric field, so that means the angle between them is 0, right? So for this one, this will be E multiplied by cosine 0, right, times the area. Since cosine 0 is equal to 1, right, you can go ahead and check your cycle for the value of that. So this will be EA. Alright, so this will be the final formula or the definition of the electric flux that passes perpendicularly to the surface of something. Okay, so how about this second example? For the second example, you're going to notice that the turn or the phi is here, no? So there's your phi, okay, is perpendicular to the electric field, right? The electric field is parallel to the surface and is perpendicular to the normal line. So writing that one down, so that would be E cosine phi multiplied by the area, and then we have, what's the value of that? Cosine 90, right? Starting from, can you imagine that, starting from the normal line, moving 90 degrees to this direction. So basically that's what? That's 90 degrees, right? So multiplied by the area. So cosine 90 is what? 0, right? So ibig sabihin, what does that mean? The electric flux that's passing through this particular orientation of an object is 0, right? Or you can also write it as, I don't know if you're familiar with this way of writing 0, right? So also signifies a null set or something, but it might confuse you because phi is also written like this. So you can just write 0 like this or like this. Okay, then of course, finally, definition of electric flux. So this is E cosine phi A for guided practice problem 3.1. So you would understand how we use it, no? So let's take a look at this first example. We have a charge that emanates an electric field of 3 times 10 raised to 3 newtons per coulomb. If this field is placed on a circular surface with the radius of 3 centimeters and is angled at 30 degrees from the surface, what is the electric flux? Okay, so let's say you have a circular surface, okay? So we have a charge that emanates an electric field. So in this case, we're going to use yellow for the electric field. By the way, the radius of the circle is 3, right? So we're just going to represent it by having letter R here. Okay, then the electric field will be represented by color yellow. So according to the problem, the electric field is angled 30 degrees from the surface, so not from the normal. Okay, so what angle would that be? That would be theta. Okay, so this is your electric field. Okay, so this will be your theta, this one here. All right, what do we need ba? What we need is of course phi, which is actually easier if you're just going to subtract it right ahead, but at least you have an understanding of how it could be done. Anyway, it looks something like this. So this is your phi. Okay, so let's try to solve for the electric flux. So the given are, first we have an electric field that has a strength of 3 times 10 raised to 3 newtons per coulomb. Okay, then we have the radius of the circle, which is 3 centimeters, which is equal to 3 times 10 raised to negative 2 meters. Next we have theta, okay, which is of course 30 degrees, but what we need is phi. So instead of that, we're going to have phi instead, which is equal to 90 minus theta, right? Which is of course 60 degrees. Okay, and then what else do we need? That's it, no? From the given. Then required is electric flux. Okay, for our equation, it will be, of course, electric flux is equal to E cosine theta, cosine phi multiplied by the area. Sorry. Okay, so there's that. All right, next is to substitute. So in this case, what would be the formula that we're going to use for area? So that would be area of the circle. Okay, so your equation now will become electric flux is equal to E cosine phi multiplied by pi r squared, right? Because this is the formula for the area of the circle. That's why I have told that you have to recall the lectures that you had in geometry classes before, as we're going to utilize a lot of area, surface area, and volume on topics about electricity. Okay, anyway, we can now substitute. So we have electric flux equal to, okay, what's our electric field? 3 times, let's make this smaller, so this will be 3 times 10 raised to 3 newtons per coulomb. Okay, multiplied by, what's our cosine phi? It's 60. Okay, so that's cosine 60 multiplied by the area. So area natin is pi multiplied by we can just place pi here, right? Or we can just place pi here. Then we have 3 times 10 raised to negative 2 meters to be squared. There. So you're going to notice the units. Okay, so for our final answer, which of course you have to solve, okay, we're going to notice that we have newtons per coulomb and meters squared as our unit. So you try to look for the final answer, alright? But the final answer would be Newton meter squared per coulombs. Alright. So you got this. Okay, so if you're going to complete the drawing of the electric field, it will be many lines that are drawn to that direction as well. Okay, but of course you're just going to take one, so it would be easier to illustrate. Alright, so let's have guided practice problem 2. Okay, so now we have a sheet of paper. Okay, so let's draw that. We have a sheet of paper. Okay, that has side measures of 300 millimeters by 200 millimeters. Alright, and is oriented so that the normal to the sheet is at an angle of 60 degrees. So you're going to notice now we have the term normal. Okay, so that means that electric field is placed at an angle of 60 degrees. Okay, so the angle here, starting from the normal going here, okay, is 60 degrees. Alright, so of course our electric field is there. Okay, so now we're going to look for the magnitude of the electric flux. So let's write the given. So for our electric field, we have 14 newtons per coulomb. Okay, for our area, it's just what? Length times width, no? So that's 300 millimeters by 200 millimeters. Okay, or you can just write length and width. Ay, by 240 pala. 240 pala to, no? This is 240. Alright, then we have the phi, which is already phi, so we don't have to convert it anymore, which is again 60 degrees. Okay, for our required, we have electric flux. Okay, for the equation, of course, it's the same thing. No? Electric flux is equal to E cosine phi multiplied by the area. So this is the equation. Okay, so now we can substitute. So electric flux is equal to 14 newtons per coulomb multiplied by cosine 60. Okay, multiplied by, so our area is 300 millimeters by 240 millimeters, so we can convert that one. Okay, so that would be 300 times 10 raised to negative 3 meters multiplied by 240 times 10 raised to negative 3 meters. So that's it. So for the answer, you can just proceed on solving this one up. Alright, so there you go. So the final answer of this will be Newton meter squared per coulomb. We'll be having a unit of Newton meter squared per coulomb. Okay, so for the third guided practice problem, and actually the fourth one as well, we're going to deal with surface area. So that will be the surface of three-dimensional objects. Okay, I'm going to do it on another video to show the derivation of how we arrived on such a formula, because you're going to meet a new way of rewriting electric flux. Okay, that's it. Thank you.